Hello and welcome to this tutorial using Maple to help us solve deflection using the double integration method. In this tutorial, we'll look back at the simply supported beam with 2-point loads that we fully solved by hand, go over the engineering conclusions, and see how we can utilize Maple to help us deal with a mathematical bit. So we're looking again at this simply supported beam with a uniform cross-section carrying 2 equal point loads. The loads are applied symmetrically at a distance a from each support, leaving a central region of a length L minus 2a. Once again, the same objectives: determine the equation of the elastic curve, the slope at a, and maximum deflection. So as a reminder, we solve this fully by hand, including all the very long maths. And here we're just going to look at the engineering decisions that need to be made before we can use Maple or any other math solving software. So let's quickly recap the double integration procedure. We assume that EI is constant within each segment of the beam, otherwise that needs to be integrated as well. The elastic curve is sketched first just to establish boundary conditions and expected behavior. We then write the expressions for the bending moment for each segment using the method of sections. Once we have that, and once we know the discontinuities and the boundary conditions, we can use Maple to perform the integration, apply those boundaries and continuity conditions, and evaluate the slope and deflection. The engineering input obviously remains exactly the same as in the hand solution. As a quick reminder, first we sketch the expected elastic curve of the beam, and because the beam is simply supported, the vertical deflection is 0 at supports A and D. The loading is symmetric, so the elastic curve is also symmetric, with a maximum deflection occurring at mid-span between the 2-point loads. Next, we need to determine the bending moment distribution along the beam. Under the 2 equal point loads, the bending moment varies linearly from A to B, remains constant between B and C, and then varies linearly again from C to D. To analyse this systematically, we divide the beam into 3 regions: Region 1 from A to B, Region 2 from B to C, and Region 3 from C to D. In each of these regions, we introduce local coordinates. So just like we did in the hand calc, in Region 1 we have coordinate x1 measured from A towards B, Region 2 we had x2 measured from B towards C, and in Region 3 we had x3 and we measured it from the right hand support D back towards C. The distances shown reflect this, so Region 1 and Region 3 both have a length of A, and the middle region has a length of L minus 2a. The local coordinates are used to write the bending moment expressions in each region before we apply the double integration method. Just a reminder of how the free body diagram looks once we've found the reactions, and of the notation for the 3 moments, just as we did in the hand calcs. This slide summarises the bending moment expressions in each region of the beam and the coordinate directions used to obtain them. If you need a reminder of how to do them, I suggest going to the tutorial where we solve this fully by hand. But we're left with this summary. In Region 1, the moment is p times x1, and this is valid from x1 between 0 and a. In Region 2, the moment is a constant p times a, and this is valid from x2 between 0 and L minus 2a. And in Region 3, where we note that the direction is going from right to left, as noted by that little arrow on the third line, the moment is p times x3, and x3 goes from 0 to a, but obviously, once again, from right to left. The arrows themselves, as you can see on this slide, are not sign conventions for the moment, they just indicate the direction. It's important for us to make sure that we know the directions when we come to look at continuity. So once again, if you want to develop the full expressions, if you want to see how these full expressions are developed, go back to the tutorial where we develop them. The next thing we need to do is express what the boundary conditions and the continuity conditions are. Let's begin with the boundary conditions at the supports. The beam is simply supported, and therefore the vertical deflection at each pin support is 0. At the left support A, the coordinate is in Region 1 and it's x1 equals 0. That gives us point A, and we know that the deflection there equals 0. So y1, the deflection in Region 1, when x1 equals 0, i.e. we're at point A, equals 0. At the right support D, we're in Region 3, so the coordinate is x3 equals 0, and that gives us the boundary condition of y3, the deflection in Region 3, when x3 equals 0, so when we're at point D is 0. This, again, is exactly the same conclusion that we reached when we did the hand analysis. We'll now state the continuity or compatibility conditions at the internal points of the beam, again, exactly as in the hand solution. So at points B and C, both deflection and slope must be continuous. This reflects the fact that the beam is physically continuous with no hinges or breaks at these locations. Starting at point B, which connects regions 1 and 2, the slope must be the same on either side of the point. So when x1 equals a, so for region 1 we're at point B, and x2 equals 0, so in region 2 we're also at point B, at that same point B, the slope y tag 1 at that point must equal the slope y tag 2 at that same point. The deflection also has to be continuous at B. So y1, when x1 equals a, so we're at point B, has to equal y2, the deflection at point 2 from region 2, which happens when x2 equals 0. In the same manner, we can move to point C, which connects regions 2 and 3. The deflection, once again, matches directly across the point, giving us that y2, when x2 equals L minus 2a, has to equal y3 when x3 equals a. For the slope at point C, though, we do need to account for the coordinate direction. The local coordinate x3 runs in the opposite direction to x2, so while the physical slope is the same, the mathematical expression will differ by a sign, and that gives us that when y tag 2, so the slope in region 2, when x2 equals L minus 2a, so at point C, has to equal minus y tag 3 when x3 equals a. Together with the two boundary conditions at the supports, these provide us 6 conditions for the 6 unknown integration constants that we know that we'll get from double integration. And from this point forward, the remaining steps are purely mathematical and will be handled by Maple. So let's now move on to Maple. I've opened a classic worksheet, just like I showed in the lecture number 3, and in this worksheet I've included a small graphic of the beam. This is just a visual reminder for me so I know what I'm solving. It's not required from Maple. The first command we use is restart. That clears any previous definitions and ensures that we're working in a clean spreadsheet. We then define the bending moment expressions for each region. So in region 1, the bending moment is m1 equals p times x1. In the middle region, region 2, the bending moment is constant, m2 equals p times a. And in region 3, the bending moment m3 is p times x3. The key point to note here is colon equals. In Maple, this assigns an expression to a variable. It tells Maple that this is the definition of the bending moment in that region, rather than something to just be evaluated immediately. You must use the equal colon sign if you want the program to recognize what m is when we come to do the integration. Note here that at the end of each command I've used a semicolon. That just means that the result of the command is then printed in blue, as you can see in the middle of the screen. If I use a colon, it is still evaluated, but it is kept in the memory. It's not expressed on screen. These moment expressions, as you can see, are exactly the same as those we obtained in the hand solution, and they'll form the starting point for the symbolic integration. We can now integrate the bending moment expressions in Maple. So for each region, the bending moment is integrated once and assigned to EI theta. So EI theta 1 for region 1, 2 for region 2, and 3 for region 3. The command is int, so integrate, and in brackets, the expression you want to integrate, so m1, m2, or m3, and by what, so by x1, x2, or x3. At this stage, we also add a constant of integration. So for region 1, C11, for region 2, C21, and for region 3, C31. The first index, as you've worked out probably, indicates the region, and the second indicates that the constant comes from the first integration. Note that these are assigned, so EI theta, and then you have the colon equal to assign that integration into that place. That means that when we use EI theta next, it already knows that it is the first integration. The next thing we do is we integrate each expression for EI theta, and we assign it to deflection EIY1, EIY2, and EIY3, depending on the region. We also introduce another set of constants, so C12, C22, and C32. As before, the first index refers to the region and the second to the order of integration. At this point, Maple is simply performing the same integrations used in the hand solution, and we're explicitly defining the symbolic expressions for EI theta and the deflection in each region. We now have 6 unknown constants, which we will determine next using the boundary and continuity conditions that we established. Let's first apply the boundary conditions. The maple command used here is subs for substitute. It replaces a variable with a specified value inside an expression. So in the first line, we substitute x1 equals 0 into the deflection expression for region 1, and we set the result equal to 0. This enforces the boundary condition that the deflection at the left support A is 0. In the second line, we substitute x3 equals 0 into the deflection expression for region 3, and again we set the result equal to 0, enforcing 0 deflection at the right support D. Maple simplifies these conditions automatically, and in this case immediately shows that the constants C12 and C32 must be 0. These are 2 of the 6 integration constants. The remaining constants are determined next using the compatibility or continuity conditions at points B and C. At this stage, we apply the compatibility condition for slope at point B. We begin by evaluating the slope expression in region 1 at point B. In region 1, point B corresponds to x1 equals a, and using the subs command, we substitute x1 equals a into the slope expression for region 1, and we store the result as equation 3a. We then evaluate the slope expression in region 2 at that same physical point. In region 2, point B corresponds to x2 equals 0. Again, using subs, we substitute x2 equals 0 into the slope expression and store this as equation 3b. Because the beam is continuous, the slope must be the same on either side of point B. The sign convention has already been accounted for in the way the slope expressions were defined, so we can equate these two expressions directly. So setting equation 3a equal to 3b gives the slope continuity equation at point B, or equation 3. In the same manner, we can apply the compatibility condition for deflection at point B. As before, we substitute x1 equals a into the deflection expression for region 1, giving us equation 4a. We then substitute x2 equals 0 into the deflection expression for region 2, giving us equation 4b. Because the beam remains continuous, the vertical displacement at B must be the same when approached from either side. Setting equation 4a equal to equation 4b gives us the deflection compatibility equation, equation 4. Next, we apply the compatibility condition for slope at point C. We begin by evaluating the slope expression in region 2 at point C. In region 2, point C corresponds to x2 equals L minus 2a. Once again, using the subs command, we substitute x2 equals L minus 2a into the slope expression for region 2, and we store it as equation 5a. We then evaluate the slope expression in region 3 at the same physical point. In region 3, point C corresponds to x3 equals a. Again, using subs, we substitute x3 equals a into the slope expression and store this as equation 5b. Because the local coordinate in region 3 runs in the opposite direction to that in region 2, the physical slope is the same, but the mathematical expressions have the opposite sign. We can therefore equate equation 5a as equaling minus equation 5b and get the slope continuity equation for point C, equation 5. And finally, we apply the compatibility condition for deflection at point C. We begin by evaluating the deflection expression in region 2 at point C, and in region 2, point C, as we mentioned, corresponds to x2 equals L minus 2a. Using the subs command, we substitute that into the deflection expression for region 2 and store the result as equation 6a. We then evaluate the deflection expression in region 2 at that same physical point. This corresponds to x3 equals a. Using subs, we substitute that into the deflection expression for region 3 and store this as equation 6b. Because the beam is continuous, the vertical deflection at point C must be the same when approached from either side, and setting equation 6a equal to equation 6b gives the deflection compatibility equation at point C. Together with the boundary conditions and compatibility conditions that we applied at point B, we now have a complete set of equations and we're ready to solve the system in Maple. So here we ask Maple to solve the full system of equations we've constructed. The solve command is used to solve 6 equations, the 2 boundary conditions and 4 compatibility equations for the 6 unknowns, C11, C12, C21, C22, C31 and C32. You can see here that the solve command has brackets, and then you open curly brackets, write all the equations you want to solve, close those curly brackets, comma, and then another set of curly brackets with all the constants that you want to solve too. We wrap the solve command inside a simplify command so that Maple returns the constants in a clean, simplified form. The resulting values are displayed here, and you can match them to the hand calculations we've done previously. At this point, Maple has determined all of the integration constants, and as expected, this includes ones that we identified earlier from the boundary conditions. So you can see here that C12 and C32 are both 0, as we expected. The assign command is then used to substitute these values back into the previously defined slope and deflection expressions automatically. From this point onwards, the constants are built directly into the expressions, and we no longer need to carry them explicitly. And here we can define the final expressions for slope in each region of the beam. Now that we know all the integration constants and we've assigned them, we can divide each of the slope expressions by EI to obtain the physical slope theta. The simplify command is used to clean up the resulting expressions, and this gives us the slope results in region 1, 2, and 3, labelled as θ1, θ2, and θ3. The expressions describe how the slope varies along the beam in each region, and we can now use them to evaluate the slope at any point of interest. And finally, we can define the final expressions for the deflection in each region of the beam. Now that we know all the integration constants, we can divide each of these expressions by EI to obtain the physical deflection y. Once again, we use the simplify command to clean up the resulting expressions, and this gives us the deflections in region 1, 2, and 3, labelled as y1, y2, and y3. Together, these expressions define the complete elastic curve of the beam and can now be used to evaluate the deflection at any point or to compare with the hand solution. So let's calculate the slope at support A and compare it with the hand calculation. We start by identifying that the slope at A is in region 1, and it is when x1 equals 0. That corresponds to support A. So using the subs command, we can sub x1 equals 0 into the slope expression for region 1, simplify it, and get the result, which Maple returns to us as minus PA brackets L minus A over 2EI. We can then compare this directly with the value that we obtained in our hand solution. Writing the hand result in a consistent form shows that the two expressions are identical. And this confirms to us that the Maple solution is consistent with the hand analysis that we already conducted, and the boundary and compatibility conditions have been applied correctly. And as a final step, we can evaluate the maximum deflection of the beam. From the hand solution, we know that the maximum deflection occurs at the midpoint of the central region. In terms of the local coordinates, that means that we are in region 2 and x2 equals L minus 2a divided by 2. Once again, using the Maple command subs, we can substitute it into the deflection expression for region 2, and we can simplify the expression and get the resulting maximum deflection as minus, open brackets, L squared minus 4a squared over 3, all that times PA, and divided by 8EI. Our hand solution result was a bit different, but we can rearrange it into the same form and see that the two expressions are identical. So once again, this confirms that the Maple solution is fully consistent with the hand calcs and that the mechanics, boundary conditions, and compatibility conditions have all been applied correctly. In this example, we had 6 constants of integration. As we saw in the hand calculations, even for a relatively simple beam, the algebra becomes quite lengthy, with many steps and many places where small errors, such as signs, can easily occur. Maple does not replace the structural mechanics or the need for engineering judgment. Instead, it provides a reliable way to handle the mathematics once the problem has been set up correctly. It allows us to focus on understanding the behavior of the structure rather than managing lengthy algebra. I hope you found that helpful, and as always, I hope to see you again for some more structural engineering.